Having established the general theoretical framework for geometrical nonlinear finite element method, now I would like to derive the tangent stiffness matrix, in particular the geometric stiffness matrix for a few structural elements, and I would like to start with the truss element. So suppose we have this truss element lying along the x direction, and it has L0 being the original length and A0 being the original cross-sectional area. Now, underloading this element may move to a different position, and the nodal positions would be simply the original nodal position plus the respective displacement vectors. We have the nodal degree of freedoms of this element being u1 v1 and u2 v2, where u1 and v1 are the nodal degree of freedoms of the first node, and the u2 v2 are those of the second node. We can express the uv along the arbitrary positions in this truss by interpolation using the shape functions n1 and a2. So n1 is the shape function for node 1, n2 is the shape function of node 2. We can write n1 as L0 minus x over L0, and n2 as simply x over L0. I would like to do a replacement variable where I replace the axial strain, which is exx, by writing as e11, because I don't like the space between the capital X that the latex put there, so I think e11 is better looking. Now, in the truss element, there is only the axial strain and stress that matters. The others are all zero, so I can simplify the internal water work to be simply written as A0L0, which is the volume, times the variation of E11, and then multiply with S11. Then I would like to express the Green-Lagrange strain along the axial direction, which is E11, and you would arrive at this form if you plug in the formula. So it has a linear term and two nonlinear terms. Next, I would like to do the variation of E11. So I have the variation first on the first term, the linear term, and then for the two nonlinear terms. The objective here is to eventually sort out the B matrix. So I would first group the common terms together. So I have 1 plus partial u over partial x, multiply with partial delta u over partial x. So this would be the same as the first two terms here. Then I would like to substitute the delta u by the shape function multiplied with delta uj, which is the nodal variations. Similarly here, so I replace delta v as nj times delta vg. So we have the Einstein summation convention, where we sum over the repeated indexes from, in this case, from 1 to 2, because we have two shape functions. Now we are very close to sorting out the B matrix, because we already have the delta uj and delta vj. The B matrix would be a row vector, so you can verify this easily. If we substitute j by 1, then delta u1 would be the variation with the first nodal degree of freedom here, and this replacing j by 1 would give us the first term, and then you can verify the rest. Now we have the B matrix, we can already obtain the material tangent stiffness matrix. But to obtain the geometric stiffness matrix, we still need to perform this partial derivative of B with respect to A. Let us rewrite B matrix in a different format. I'm going to shift this to the front of the bracket, and then I'm going to express U by this expression using the shape function interpolation and nodal degree of freedoms. And using the Einstein convention, I write it as nj-uj. Similarly, for V, I replace it with the nj-vg, and I'll do the same for the third and the fourth term. Then the B transpose would be a vertical vector, and the partial derivative of B transpose with respect to A, our degree of freedom vector, would be a matrix. The ij term of this matrix would correspond to partial of bi over partial of aj. Let's take an example. So A here, I just rewrite here for reference. So A is a U1, V1, U2, V2 transpose. The first term of this matrix, which is partial B1 over partial A1, would correspond to taking the partial derivative of this term with respect to the first nodal degree of freedom, which would be U1. And then we will be left only with this term multiplied with this term when j equals to 1, which gives us this term. And if we substitute the expression of A1 and 1 into this term, then we will be left with simply 1 over L0 squared. Then we can repeat the same procedure for the other terms and fill up the entire matrix. After having performed this operation, and we can find the expression of this matrix, and it's a symmetric matrix made of only 1, 0, minus 1, and divided by L0 squared. Because we have simplified internal water work to contain only S11, so this is the expression of geometric tangent stiffness matrix in terms of partial B transpose over partial A. We can define a P0, which is A0 times S11. This is the axial force applied on the truss in the initial configuration. So under the small strain assumption, this P0 is approximately the same as the amplitude applied force P. This we have talked about in the first part of this lecture, where we showed the meaning of second Euler curve stress on the truss. Now, filling in this expression by the matrix expression, we can arrive at the final expression of geometric stiffness matrix for the truss element. You can see that this term here is constant. L0 is a parameter of the geometry of the bar, and then is a function of P0, which is the applied force. Next, let's move on to a more complicated element type, which is a beam element, in particular the Euler-Bernoulli beam element. For the beam element, it is well established that it has two nodes, and for each node we have a deflection degree of freedom W and rotation degree of freedom theta. And we have a shape function having 4 terms. And in Euler-Bernoulli beam theory, what is normal remains normal to the neutral axis, and it remains straight, which means that we can express our U, which is the axial displacement, by this expression. And W, we assume that is only a function of the x. Now we can replace W by the shape function multiplied with the degree of freedom vector. And then we do the variation of W, and we have n times delta A. Similarly, as in the case of truss, there is only the axial stress and strain that, which are of interest, and the others are 0, under the assumption of Euler-Bernoulli beam theory. So we can simplify our internal water work to be the integral of delta E11 multiplied with S11. So again, I replace the variable here where E11, S11 means the axial strain and stress around the x direction. Again, we calculate the E11, the Green-Lagrange strain. We have a linear term and 2 nonlinear terms. Now, because of this expression, I can plug in, and I replace the U with this expression, and I obtain this expression of E11 in terms of W only. Now, this is very small because the Euler-Bernoulli beam theory applies on cylinder beam, so we can neglect it. So we are left only with these 2 terms. Now I perform the variation of E11 so that eventually I would be able to sort out the B matrix. And having obtained the variation, I would like to substitute the delta W by n times delta A. Now I've sorted out the delta A, and we have our B matrix, which is within the bracket. Having obtained B matrix, we can already calculate the material tangent stiffness matrix, but again, we need to do the partial derivative with respect to A to obtain the geometric tangent stiffness matrix. For that, let us take a look at the ith term of B. So B is again a row vector. This is the column vector. Then their product gives a scalar. So n here is a row vector. This is our shape function matrix. Now the ith term of B is simply plugging in the ith term of n and then we arrive at this expression. To facilitate our partial derivative operation later, let us express W by its shape function multiplied with the nodal degree freedom vector. And I again use the Einstein summation convention. So W would be Nj times Aj, where I sum over J from 1 to 4. Now, if you look at this expression, when I take the partial derivative of Bi with respect to Aj, I would be left with only this term here. So this is the matrix, as I mentioned earlier. The Ij term would correspond to partial derivative of Bi with respect to Aj, and this is the term that is left. We can substitute the expression into the full expression of our tangent stiffness matrix. Again, here we have already simplified the internal waterwork so that we have only the S11 term here. We can see that the A0, which is the cross-sectional area of the beam, we can see that the B matrix is a function of our shape function, and shape function is only a function of the axial coordinates x. It's independent of the cross-sectional area A. So we can sort out this term outside of this integral, and we leave inside only S11, and we perform the integral of S11, we obtain our axial force P0. So we can bring this P0 outside of the integral over L. This is, of course, assuming that the axial applied force is constant through the length of this beam. Then we arrive at this expression. Now, this is the ijth component of this matrix, and we know that ijth component of this partial B transposer of partial A is simply this term. For this Euler-Brillouin beam element, these shape functions are very well established. These are the expressions of the shape functions. You can find these expressions in most of the finite element books. So as long as there is a section on beam elements, most likely you will find these shape functions. In order for me to be to calculate this tangent stiffness matrix, I need to take the partial derivative of shape functions with respect to the material coordinates capital X. But these shape functions are expressed in the natural coordinates cosine. So we need to do the mapping. So we take the partial derivative with respect to cosine, and then we multiply with the partial derivative of cosine with respect to capital X. This is the inverse of Jacobian that we talk about. Basically, when we map a line element to its natural coordinates, we are changing in length. That's the only thing that is changing. And the natural coordinates always start from -1 to 1. So the Jacobian would be L0 over 2, and the inverse of Jacobian would be 2 over L0. So that's where the 2 over L0 comes from. Now we can plug in the expression of Ni and calculate partial of Ni over partial of capital X using this formula, and then do the integration over L0. And then you would arrive eventually at this expression. It is again a symmetric matrix, and is only a function of the geometry parameter, which is L0, and the loading, axial loading, P0. Next, let's look at an even more complicated element, which is plate element. And here we assume classical plate theory for this element. In classical plate theory, W, which is our deflection, is a function of x, y only. And we have these expressions of U and V based on the Kirchhoff-Love hypothesis, which means that what is normal to the midplane remains normal after deformation. So this is the consistent assumption with respect to Euler-Bernoulli beam theory. Now we express W in terms of a shape function multiplied with nodal degree freedom vector. And we can again calculate the variation of W in terms of a shape function multiplied with a variation of the nodal degree freedom vector. Then the next step is to simplify the internal waterwork. We remove all the zero strain terms. So with this expression, we are left only with the axial strains in both directions, as well as the in-plane strain term. and the implant strain has 1, 2 as well as 2, 1, and they are the same. So eventually we will have a multiplication of 2 here in terms of shear strain energy. And next is we follow the same drill. We calculate the Green-Lagrange strain. There is a linear term and nonlinear term, and we repeat the same procedure for the other strain terms. And then we calculate their variation with the objective of sorting out the B matrix. Eventually this would give us the B matrix. And this is with respect to the axial strain in the x direction. We can repeat the same procedure and sort out the B matrix for the axial strain along the y direction as well as the for the shear strain. Having obtained this B matrix, we need to further take their partial derivatives with respect to A to finally arrive at our geometric tangent stiffness matrix. And for that, we follow the same step. We first look at the ith term of the B matrix, let's say along the x direction. This is simply plugging in the ith term of n, and then we would arrive at this expression. To facilitate our partial derivative operation with respect to nodal degree of freedoms, we replace W by shape function multiplied with the nodal degree of freedom vector, and we write the indicial notation by Einstein summation convention. So we have now W equals Nj Aj. Similarly, we do the same for the other B matrix terms. So for the axial strain along the y direction, we have exactly the same expression, except that now we replaced capital X with capital Y. For the implant shear strain, is slightly more complicated, but you can replace W in these two terms by Nj Aj, and then you sort out the common term Aj, and you will arrive at this expression. Next, we take the partial derivative of the ith term of B matrix with respect to the jth term of A. Then we are left with only these terms for the partial derivative. You can verify this yourself. We can define similarly the force intensities. So in plate theory, we have these quantities like axial force intensities along the x and y direction and the shear force intensities. Then with this defined, we can express our geometric tangent stiffness in terms of these quantities multiplied with our axial force intensities. They are sometimes called membrane forces. We can write them in a more simplified form, where we have multiplication of 3 matrices. You will arrive at the same expression. We will not substitute the exact expression of shape functions, but you can do it with a certain chosen shape function for the plate element. There are different choices for this, so I will not present these details, but just to give you the general expression. So once you finalize on the choice of shape function, you can plug in and calculate the exact expression of this geometric tangent stiffness matrix. To summarize on the steps in deriving the tangent stiffness matrix for a geometric nonlinear finite element, we start with simplifying the weak form and return only the non-zero strain terms. This should be simplified. And then we find the expressions of the Green-Lagrange strain components, for instance E11 in truss and beam. Then we do the variations and sort out the B matrix. That's the most important thing. So we calculate the variation, and when we sort out the variation of the nodal degree of freedom vector, and we are left with a B matrix. After obtaining the B matrix, we would then be able to calculate the material tangent stiffness matrix, which is B transpose CB integral over omega 0. But we still need to take the partial derivative with respect to nodal degree of freedom to obtain the geometric tangent stiffness. For that, we can take the partial derivative component by component and eventually sum up to obtain the full expression of geometric tangent stiffness. In summary, these are the 3 elements that we've covered, and we can see that the geometric stiffness scales with the axial or membrane loading. So the higher the axial force or membrane force intensities, the higher is the geometric tangent stiffness. This property of geometric tangent stiffness is very important when we analyze buckling, which I'm going to show you later.